Hey, welcome to this video. In this video I would like to talk about the question how fast do particles settle and which forces act on particles driving this movement. Therefore, we have these three topics I would like to discuss, and this is first an insight into the lithium production as a small example about the application of forces and the question about settling velocities. And from this we would go to the question which forces actually act on particles. And finally we can then calculate the settling velocity of a particle. And I would like to start with this example. This is a lithium ion battery, or the principle, so a battery like this, right? A very simple battery. And it works that we have a cathode and an anode, right? And between the anode and cathode, as you see here, the lithium ions travel through an electrolyte. And in the way they travel, we can charge or discharge the battery. And if we have a consumer here, which could be your mobile phone or a car or a laptop, then the electrons can make your mobile phone work. And if you take a little bit more and look into these schematics, so we have here carbon, right? And this is graphite. And graphite is really, really good for the anode, because when you charge your battery, the lithium ions travel through the anode, and it works like small boxes between the graphite, and they are really like two-dimensional plates, like here, a piece of paper, and then the ions go between. And so if you charge, the ions travel, and on the other hand, if you discharge, the ions go back, and then they go here into the cathode. And now we take a look at the cathode. So we see it's an oxide, and we see it's a metal oxide. So the material we are using here is a lithium metal oxide, and there are different combinations, as you see here: cobalt, nickel, mangan, which you can use as metals. And these lithium metal oxide are in the form of particles in the battery. So particles, especially lithium-based particles, are extremely important for lithium batteries. And if we take a look here, this is the global lithium battery production capacity. And the study is from 2023. So not that old, and you see this is the data for 2022, and then expected, and we expect a huge growth in the battery production. And you also see it separated for regions, and we see a very clear dominance about Asia in the lithium battery production, right? The EU is not really good, and we try to increase the amount of production capacity, but basically the most of the lithium batteries are produced within Asia. And here you see the companies, and it goes basically to these three countries: China, South Korea, and Japan. And here are companies probably all of you know, right? CATL, BYD, or here we have LG, and here in Japan Panasonic, and that's the rest. So we have a very clear dominance about these three countries in the lithium battery production. And the batteries are not just you take the lithium and put it into the batteries, but what you see here is the lithium in different forms. So we have mineral, we have lithium metal, we have lithium hydroxide, and we have lithium carbonate. So to make the batteries, we need lithium, right? But lithium is also used for different other stuff, like in glass industry, or also in medical applications. So to get all these produce all these products, and we have this increasing amount of production capacity, we need more and more lithium. And this lithium has to come from somewhere. And when we mine the lithium, we process is into these two materials mainly: lithium carbonate and lithium hydroxide, because these one can very easily transformed in the lithium you need for your special application. Could be a metal oxide, could be something else, and they are very easy to produce and to handle. And here we see that this amount also is expected to increase. So basically we will produce more lithium carbonate, which we get from the soil or from recycling maybe, and also more lithium hydroxide, while especially this lithium hydroxide amount is increasing. And then we can give it to the companies like Panasonic, LG, and so on. And they use these materials to make battery material and then batteries out of it. So how do we get the lithium? And here you see one picture, and basically there are two ways. If we skip out the recycling, because most of the lithium is get from the nature, and one thing is mining, right? So we mine lithium, and this is, for example, mainly done in Australia. Australia is a very big lithium production country, and mainly they do mining. And the second possibility we have are these brines, right? So we take water, we evaporate the water, and the lithium is enriched, and then we get the lithium from this groundwater here. And this is a very nice graphic, shows you the cost. Here we have on the x-axis the production capacity, right? And these are different companies using the brine technique or the mineral technique. And you see a very clear difference between both, and this is basically the price. So the brine is much cheaper, or in the brine it is much cheaper to produce lithium, so dollar per tons, compared to mining from minerals. I don't judge it ecologically, and there is no statement ecologically here. This is just the economy. And if we look now into this brine process, and this is a very nice patent, and in the patent we see the mining of lithium carbonate by brines. So this is the lithium as a material which we can sell then to battery producers or other companies. And therefore we have these solar evaporated brines. So basically what you see here on this picture, and you see the enrichment, you see the change in color. But what not happens is you don't get the final lithium carbonate here, right? So you have still to process it. And what you do is you take this enriched brine, and then you see here a very complicated process, right? So a lot of things happening along the process till at the end, when I go through here, we get our lithium carbonate. And the question is, what happens? And this is what you see here in this table. And this is how the brine, the content, that's the word I'm looking at, the content of the brine from Atacama salt mine. And then you see, oh, we have lithium in here, 5.9%, but we also have boron, we have chlorine, we have magnesium, we have potassium, and so on. And we don't want to have these things because we want to have pure lithium carbonate. So what do we have to do? We have to purify. And we purify, and this is what you see here, by separating the single parts out of the brine till we get clean brine, which we can use for our lithium carbonate. And the cleaning works quite similar along the process. So basically what you do here, and I really like the patent or the depiction because it shows very nicely different parts of chemical engineering. So here we see a reactor. And in the reactor, the brine goes in and we mix it with 35 weight% hydrochloric acid. And you also see a mixer. And we set the pH to 1.8, 10 degrees Celsius, and we wait 12 hours. And then 71% or around 70% of the boron will precipitate as boron acid. So we will get boron acid particles in here. And these boron acid particles we put into this settling tank here, or a thickening tank. And in the thickening tank we just wait, and then the boron acid particles, they just settle down. And then we put these thick fluid or liquid into a filter, and here we can filter out the bore acid particles. So this means the amount of bore is reduced, right? Boron, sorry. But since it's only 70% which is precipitated from 0.8%, we still have to do a second separation step, and this is here an extraction step. And extraction is from a different topic of chemical engineering, but maybe you have seen these diagrams how to separate. It's a liquid separation, and after the extraction we will get a brine with 0.005 weight% boron. So the boron is out. And along the rest of the patent, all the other parts are separated out, and this means at one point we will have a purified brine which has an enriched amount of, by percent, enriched amount of lithium. And now we can precipitate the lithium, and then we go through separation steps, then it goes into a filter, and from the filter we take our filter cake, which consists mainly out of lithium carbonate particles, then we dry them, and here we get our final product with a purity of 99.2%. So, and in this process we have a lot of very interesting unit operations. So we have the mixing and precipitation here, we have the drying here, we have a filter here. But I would like to highlight now this thickening tank, because we create particles, and the amount of particles in the liquid is quite low compared to what we have later in the filter. So what do? We just wait that the particles settle down. And my question now is, if I create these lithium carbonate particles, how long do I have to wait till all of them are settled and I can put the enriched liquid into the filter, right? And this is what you see here. It's a more or less schematic picture of a thickening tank. So the liquid with the particles comes in, and then we have the sedimentation zone, and here the amount of particle enriches, while here we have liquid which has low lithium carbonate particles, and this can be taken out and used for other things. So if we take a look where the particles, there they are, right? They are somewhere here, and they have a so-called terminal settling velocity. The terminal settling velocity already has a assumption in it, what we will see. But if I want to answer now the question, how long do I have to wait till the particle travels down here and is settled down in my thickening tank? I just have to look at one particle, right? So I have one particle here, and there's already an assumption. No, there are multiple assumptions, but one assumption is my particle is a sphere. Another assumption is only one particle, so the particles don't interact with each other. Particle is in water, has a certain diameter. And to get to the velocity, I make now use of acting forces. So the question is, which forces act on particles? And there are a lot of forces, but we have to decide which are relevant. And one force for sure will act is the gravity, right? The gravity will pull the particle down along the gravitational field, and the gravity is mass times g, and g is gravitational acceleration, right? And in particle technology, we don't express it by mass, but what we do normally, especially if we have the spherical assumption, right? So we have a sphere, then we describe the sphere by the diameter. Because if you look back into the videos of particle size distributions and particle sizes, the diameter is the question. So this is the number we normally know. And the diameter of a sphere is the density, or let's say start here, is pi divided by 6 times 3 times the diameter cube. You have to be careful, because often you also find the radius. Then it's 4 divided by 3 pi radius cube. And you can make very simply errors with mixing these equations, right? I prefer to work with the diameter. If you work with the radius, you have to rearrange the equation. So the sphere is pi divided by 6 diameter cube. And to get the mass, because this is the volume, we have to multiply the volume with the density of the particle. And then we have the mass, right? Mass is density of the particle times volume. Volume is p divided by 6 d cube, and then times g. That's the gravity. And then we have a counterforce to the gravity, and the counterforce to the gravity is the buoyancy. And the buoyancy is basically the same equation. It's mass times g. But the difference from the buoyancy to the gravity is this density here, right? Because the fluid wants to go where the particle is. So it's a pressure from the fluid basically. And the pressure is on top different than on the bottom. And then we have a resulting force upwards. So we have again mass times G, and the mass is the volume times the density, but the density of the fluid times G. So now we can take a look, and we see that the buoyancy is smaller than the gravity, and this makes sense because the density of the fluid is water is smaller than the density of the solid. However, if you have a bubble, the same picture, the same model can be applied, right? And then the buoyancy would be larger because we have now a lower density of the gas bubble than the liquid, right? So we can apply this for all kind of settings and explain if something rises or falls. And now we see that there is a discrepancy between the errors, the length of the errors. This means there's still one force missing, because if this would be all forces, we would have acceleration. Acceleration is neglected here, and one force we have to consider is the drag force. And the drag force is basically the drag from the fluid, because the particle settles down, it has higher gravity than buoyancy, and then the fluid moves around and kind of breaks or tries to stop the particle. And this is described by the drag force. And I will make an additional video just about explaining the drag force, because drag force is a little bit more complicated. But what you see here is the so-called Stokes equation. So this is a very simple, or it's already an assumption, and it's a very easy equation, because the Stokes equation is 3 times pi times the diameter. This is the viscosity of the fluid times the velocity. And these are all the forces we need to consider. The rest of the forces we ignore. There could be agglomeration, but I said there is only one particle. We don't look at electrostatic or something, and we don't look at acceleration. We say there is a terminal settling velocity, so steady state. And what we have to do now is a force balance. So we balance these 3 forces, and this means basically Fg equals F buoyancy plus drag force, right? These two equals these two, and I try to also make it correct in the image. Then we just have to put the numbers into the equation. We know what is Fg, we know what is Fb, we know what is Fd, put it in here. And the question I had is, how long do we need to wait, or what is the settling velocity? So basically we are aiming for this variable, right? So we want to know what is the velocity. And therefore we reshape the equation. The first thing what we do is we make minus this term, then this term goes here, and then we can put everything out of the brackets. So we have the density of the particle minus the density of the fluid in brackets, and then times pi divided by 6 d cubed g, and on the other hand we have 3 pi dp viscosity and velocity. And if we now divide by all this and make a little bit calculation with the number, we get these final equation, and this is the velocity, and this is basically the difference in density times g times particle diameter squared divided by 18. The 18 comes from these numbers, and the viscosity of the fluid. And this is the velocity, and here now we have the t, terminal settling velocity of the particle, for example lithium carbonate particle in a thickening tank, and the terminal velocity means we don't have acceleration. The particle already has its final velocity. Okay, so if you want to recapture a little bit and task or train your knowledge, there are 3 things you could do. And the first is that you set up the acting forces for your own. So think about the question without the video and think about the forces and try to write down which forces act. And then derive the equation for the terminal settling velocity from the force balance. So you do step by step what we did. And then the last question is, calculate the terminal settling velocity for a 20 micron sized lithium carbonate particle in water. What time does it need to settle 2 meters? So we precipitate a 20 micron lithium carbonate particle, and now I want to know how fast will it settle and how much time does it need to settle 2 meters. With this, I'm at the end of the video, and I hope you learned a little bit about the lithium production and why lithium production is not only important for our mobile phones, but also interesting in particle technology. You got an insight about which forces act on particles, especially when it comes to settling, and how we calculate the settling velocity. So with this, I hope you liked the video, and if you have any questions, just let me know.